All right, folks, here we are in chapter two in a nutshell. The topic here is inference. I'll define that for you in just a moment. But perhaps I should say a word about where this belongs in the class. This class is a proof class, as I believe I mentioned in chapter one. And the basic unit in a proof, the basic sort of move that we make in a proof is called an inference. So that's the topic of this chapter. And then in the next chapter, we'll actually begin to give some of the proofs of the class, some of the initial core proofs. Now, before we begin to talk about inference, we need to talk a little bit about postulates, actually, more than a little bit. This will be part of the way that we actually make the inferences that we do. Now, what is a postulate? A postulate is an assumption that we will make that typically concerns relationships between geometrical entities that we have defined. Now, some are also algebraic as well, but the geometrical ones are about the objects defined in chapter one. Now, when I say assumption, you might well worry that, well, why would we want to make assumptions in this class? I thought this was a proof class. But don't worry, I believe that you'll find all of the postulates that I offer to you that they are obviously true, and then we will use them in the inferences that we make, which will together go to create the proofs that we will do later on. Now, as for the postulates for the year, let me direct you to the website, the site for the class, that is thinklogical.net. You will find a link there that says definitions, postulates, theorems, constructions. All the postulates that I have to offer, all the ones that we'll talk about here and the others throughout the course are there. And as well, all the definitions that I gave you in chapter one, as well as the other definitions that we present throughout the year are there. So know about that page on my site, and I would actually suggest that you go there, open up the PDFs and print them out. They're really good to have right in front of you as you do your work. All right, so, oops, didn't mean to do that. So let us now present some postulates. The initial postulates that we will consider are geometrical in nature. After that, we will consider some that are algebraic. So here is the first of our geometrical postulates called the line existence postulate. We often use abbreviations for postulates, and this we will call the LAP. And what it says is this: if we are given 2 points, then we know that there exists a line that passes through them, and this line is unique. So for instance, let us say that we are given points A and B, as in the diagram below. We know then that a line passes through them, and we know that only one such line passes through them, and this, of course, is what we mean by unique. And we will use this quite regularly in the work that we do throughout this class. And perhaps it will seem just simply obviously true and perhaps not very useful, but it is actually quite extraordinarily useful, as you will see. Now, next, the ruler postulate. It says, first of all, that every segment has a length, and that should seem obviously true. Remember the distinction that we made previously between a segment and its length. A segment is a geometrical object, of course, composed of points, as every geometrical object is composed of points. However, the length of a segment is a number. So with every segment, we have an associated number that gives its length. And now the second part of the postulate, given a line and a length, we may carve off from that line a segment of that length wherever we choose. So if we wanted a picture, and I'll draw you one, let us say that we had, for instance, I don't know, this particular line. Ooh, I drew that extraordinarily straight. I'm proud of myself. Let us say that we had the length A, and we wish to carve off, we wish to carve off a particular length from that, let us say 12. What this says, or one particular application of this postulate, says that we may then choose points on that line, let us call them perhaps F and G, such that the length of that segment that we carved off is 12, and we can indicate that on the diagram as well. So it says what should be very natural to you, that if we have enough length, and of course we would have enough length in the line, we can carve off whatever portion of that we want. All right, so here are other examples of the ruler postulates, ones that will be quite important to us. So let's say that we're given line segment AB. Tell you what, I'll draw a little picture to go with this. So let us say that we are given line segment AB. Ooh, and that's not nearly so straight, is it? The ruler postulate will tell us that there exists a point C on AB such that the length of AC is the same as CB is half of AB. That is, we may place a point C in the interior of AB such that we have split AB up into 2 equal parts. That will be the midpoint of them. So an immediate application of the ruler postulate guarantees the existence of midpoints. Here's another common application of the ruler postulate, one that we'll see in the next chapter. It will be crucial in some proofs that we do. So let us say that we have a segment AB. I tell you what, I'll draw us a little picture. So here we have a segment AB. And let us say also that we have a segment BC. And let us say third, that the length of AB is greater than the length of BC. So let's say that we then have a BC such that the length of AB is greater than the length of AC. Now, another application of the ruler postulate tells us that we can place a point D. I'll tell you what, I'll do this in a different color. We may place a point D, how about black? We may place a point D on AB such that AD is equal to BC. We can actually mark that in the diagram as such. So that says what should seem obviously true to you. If you have one length that is greater than another, then you can choose a portion of the longer that is equal to the smaller. Segment addition postulate, and our abbreviation here is SAP. And it says this: if we have a line segment AB and point C is on that segment between A and B, then AC plus CB is equal to AB. And a very simple way to understand this is that when you place that point C in the interior, you break AB up into two parts, and then the whole AB is the sum of the two parts AC plus CB. So whole is sum of parts, and that should seem quite obviously true. Now, the protractor postulate. This plays the very same role for angles that the ruler postulate played for segments. So it says, first of all, that every angle has a measure between 0 and 360, which no doubt you will find obviously true. And it also says that if we're given a ray and a particular measure that we wish to create, then we may construct a second ray coterminal with the first such that the angle that results has the desired measure. So just as an example of the second part of this definition, I guess we're on black now. Let us say that we have a ray. We'll give it a name. We'll call it ray AB. And you remember, of course, in ray names, we always place the endpoint first, and then the second letter is always some other point on the ray. And let us say that we wish to produce an angle of measure 30 degrees. So that's like the given here, the ray AB and the measure that we wish to achieve of 30 degrees. Then what this says is that we may construct a second coterminal ray, let us call it AC, such that the measure of the angle that results, which will be BAC in this case, is that desired measure. So we can create segments of any desired length, and we can create angles of any desired length. Now, I won't take the time to talk about consequences of the protractor postulate or applications of it, because they're exactly similar to the ones of the ruler postulate. With the ruler postulate, we had a guarantee of the existence of midpoints. So with the protractor postulate, we have a guarantee of the existence of angle bisectors. With the ruler postulate, we knew that if one segment was greater than another, then we could carve off a piece of the larger that was equal to the smaller. It's the same is true with angles as well by the protractor postulate. If we have one angle that is greater than another, then we can carve off by introduction of another ray a piece of the larger angle that is equal to the smaller. All right, angle addition postulate. This is very much like the segment addition postulate, but of course it's about angles. So what we do in this case is we take an angle, pictured here, angle ABC, then we place a ray through its interior, ray BP, that splits that original angle ABC up into two parts, and then we say the whole ABC is the sum of the two parts. That is, the measure of ABC is equal to the measure of ABP. How about we go back to red? This is the measure of ABP as marked, plus the measure of PBC. Okay, so once again, this just simply says the whole is the sum of the parts, but now it says it about angles instead of about segments. And like all the postulates that we've looked at, you should find this quite obviously true. Now, next postulate is the straight angle postulate, and it has two parts. It says that all straight angles measure 180 degrees, and only straight angles measure 180 degrees. And another way to put it is this, perhaps I should do this, and allow me to abbreviate. So if straight, then 180 degrees, that's the portion that says all straight angles measure 180 degrees, and if we have an angle that measures 180 degrees, then that angle is straight. So the straight angle postulate says says both of these. Okay, it says both the statement if straight then 180 and the reverse of that, if 180 then straight. Let me point something out to you here that is of importance to us. It will make a real difference in the proofs that we give in the next chapter. Notice that this postulate is not the definition of straight angle. The definition of straight angle says only that a straight angle is one whose two sides form a line. The definition makes absolutely no mention of the measure of straight angles. Instead, the information about the measure of straight angles is contained in the straight angle postulate. Now, let's turn to the algebraic postulates. You will find these all quite familiar to you. They were present in your algebra class in one form or another. Now, these are not like the complete list of algebraic postulates. That list is much longer than what I will give. Instead, I will name those that we most commonly use, and then I'll, in a few minutes, say a few words about others that will come up more rarely. So the first of our algebraic postulates is called reflexivity. It says that for all x is equal to x, or in plain English, every quantity is equal to itself. And of course, you will find this quite obviously true, and you might well wonder how this could be useful. You will see, I promise, in chapter 4 on a topic called congruence, where this comes up, and it will be absolutely essential for us. Here are examples of reflexivity. This length of segment AB is equal to the length of segment AB. Or if we switch to angles, the measure of angle ABC is equal to the measure of angle ABC. Every quantity is equal to itself. Now, the transitivity of equality, which will come up quite often, it's one of the most important moves that we will make in our proofs. And what it says is this: if you have three quantities, x and y and z, and if x is equal to y and y is equal to z, then it follows that x is equal to z. That is, if one quantity is equal to a second, and the second is equal to a third, that second is equal to a third, then first and third are equal. Here's Euclid's formulation. Things equal to the same thing are equal to one another. And notice how that does apply. If you look back up at the first line, both x and z are equal to y. That is, we have things equal to the same thing. And then we say that those two things, that is x and z, are equal to one another. And here's an example. Let us say that segment AB has the same length as segment EF, and that segment EF has the same length as segment IJ. Then it follows by the transitivity of equality that segment AB is equal to segment IJ. Substitution. This is an incredibly powerful rule, algebraic postulate that gets used in many contexts, and we'll have to see those different contexts to become accustomed to how precisely it applies. But what it says is this: if we have an equality, like the equality x is equal to y, then any expression or equation anywhere at all where we find the x, we may replace it with the y. Substitution is a kind of replacement postulate. When you have equality, you can replace one with the other. So here are some examples, and this will perhaps seem a little bit more complex. So let us say that we know that x is equal to y and that x is greater than z. It follows by substitution that y is greater than z. And how did that happen? Well, consider the inequality x greater than z. Well, that x we know is equal to y, and since it is equal to the y, we may substitute y for it. And when we do, we get y is greater than z. So that's an example of substitution. Now, you might think that this is just transitivity again, but it absolutely is not. Let's look back at transitivity. The transitivity of equality, the kind of transitivity that I introduced to you, we'll see others later on, but for now, just the transitivity of equality. Notice that we had two equations. We had x equal to y and y equal to z. Okay, transitivity of equality requires that we begin with two equations. Notice that in our application of substitution, the first of the applications, we did not have two equations. We instead had x equals y and x greater than z. So that couldn't have been transitivity. All right, let's look at the second example of substitution. That is, if x is 180 degrees over 2, then x is equal to 90. Now, no doubt you believe this is true. And as for the rule that allows us to make this inference, to move from x equals 180 over 2 to x equals 90, well, that's substitution. And how precisely does that go? Well, consider the 180 degrees over 2. We know that that is equal to 90. Just sort of basic mathematical knowledge here. We know that it's equal to 90. And since it is equal to 90, we can replace it with the 90. And when we do replace 180 over 2 with 90, we get the equation x is equal to 90 degrees. So remember this. This, of course, looks to you like algebraic simplification, and it is. So know that anything that would count as simplification from your Algebra 1 days, we will, in this class, call substitution. Now, here are some other common algebraic moves that we will make. They concern addition, subtraction, multiplication, division. So let us say that we know that x is equal to y and that a is equal to b. Then x plus a is equal to y plus b. That is equals added to equals are equals. Also, x minus a is equal to y minus b. That is equals subtracted from equals are equals. Third, a times x is equal to b times y. That is equals multiplied by equals are equals. And then finally, x over a is equal to y over b. Where, of course, a is not equal to 0 because we cannot divide by 0. And the English formulation of that, which is plain English formulation, which is also Euclid's formulation, is that equals divided by equals are equal. Now, law of trichotomy. Perhaps you've never actually encountered this before, but like the others, I think you will find it obviously true. And it says this: let us say that we have two quantities, x and y. Then one of three possibilities obtains. Either x is equal to y, or x is less than y, or x is greater than y. That is, when we actually compare two quantities together, we must have one of these three possibilities. So, for instance, let us say that we know that the measure of ABC is not less than 90 and it's not greater than 90. It will follow that it equals exactly 90. And this is a move that we will make later on when we do our proofs. We'll wish to know, for instance, that another kind of example, that let's say one quantity is greater than another. How will we actually get there? Well, we'll rule out inequality. We'll rule out that one is less, the first is less than the other, so it will have to then follow that the first is greater than the other. So whenever you rule out two, the third must obtain, and that is the law of trichotomy. Now, as for other algebraic postulates, and of course there are others like distribution, if they ever come up, and they will occasionally, we'll simply give their usual names. Distribution, like I said, is one. Association comes up in a couple of instances as well. But since they come up so seldom, I don't think it's important for us to stop and talk about them and give examples. All right, so what is all this about? All these definitions that we gave in Chapter 1, all these postulates that we have now given in Chapter 2, what do they do for us? Well, here's a somewhat metaphorical way to put what it is that they do. They are engines of inference. That is, they allow us to make inferences. Now, what is an inference? Well, an inference takes us from one statement to another, so that the second statement really does follow from the first. That is, if the first is true, the second must be true as well. And indeed will follow by some definition, postulate, or theorem. Now, we haven't encountered the concept of theorem yet, and we won't until Chapter 3. So let us restrict ourselves at the start to simply definitions and postulates. So when we say inference, we mean that we have two statements in which the second follows from the first by the application of some definition or postulate. Now, I know that's sort of quite abstract, and we need examples, so let us have examples. I have quite a few for you. So my question is this: do we have a genuine inference? That is, does the second statement follow from the first? And if so, by what definition or postulate? Okay, so notice the structure of what I've given to you. I've given you two statements. Points F and G are given. Second statement, a unique line exists that passes through them. And I have linked these two statements by the word thus. Thus, I have asserted that we have a genuine inference from the first to the second. That is, the second follows from the first. So what I wish to know is whether that's correct, whether the second does really follow from the first, and if it does, by application of which definition or postulate does it follow? Well, this is simply the line existence postulate. Okay, so let's see. I thought I could make this pop up on my slideshow. I guess not. So I'll simply write it out. Or maybe I can. Let me give it a shot here. I had set it up so that the answer could actually appear. Oh, there it is. Yes, this does follow, and it follows by the line existence postulate. If we are given 2 points, then the line existence postulate says that a line does exist that passes through them, and the line is unique. So yes, it follows by the line existence postulate. How about this one? The two statements are angles 1 and 2 form a linear pair, And second, angles 1 and 2 are both right. And I wish to know whether the second follows from the first, and if so, by what definition or postulate. And the answer is no, it does not follow. Linear pairs don't have to be right. Remember what a linear pair is. I'll draw one for you. Oops. I'll draw one for you. So you remember how we get a linear pair, right? We have a pair of adjacent angles whose non-common sides form a line. So there are the non-common sides. And I have now created two adjacent angles whose non-common sides form that line. And it's entirely possible that you have something like, I don't know, 120 and 60 degrees, right? If that 120 degree and 60 degree angle, if they're arranged in this way, they are a linear pair, but they're not right angles, right? So it's entirely possible for the first statement to be true, but the second statement false. So the second doesn't follow from the first. And so, no, we do not have a genuine inference. All right, so here's our third example. The first statement is this: AB is equal to MN, and FG is equal to MN. The second statement is AB equal to FG. Do we have a genuine inference? That is, does the second statement follow from the first? And the answer in this case is yes. This is simply the transitivity of equality. If we have two quantities, that is AB and FG, both equal to the same third quantity, that is Mn, then it follows that the first two, AB and FG, are equal to one another. So yes, follows by the transitivity of equality. All right, how about this one? B is the midpoint of segment AC, thus AB is equal to CB. Now let me make a recommendation to you. If you feel any need at all to have a diagram, but one has not been drawn for you, then simply draw the diagram. So in this case, we have a segment AC, so I will draw that. This is something into which you should establish the habit here, that draw the diagram that goes along with the verbal description. So we have segment AC, and we have B as the midpoint of segment AC, which means, of course, that it's on AC, so that the two pieces, AB and BC, are equal to one another. And so, yeah, that does follow. AB is equal to CB, and that follows by the definition of midpoint, okay? That's simply what the definition is. Okay, how about the other way around? Let us say that we know that AB is equal to CB. Does it follow that C is the midpoint of segment AC? And typically students will say, yes, it does follow. But when they have said this, they have made an assumption which they were not told that they could make. They have made the assumption that the points A and B and C are collinear. But there's no reason to think that it has to be true. You're not told that it's true. So let us not assume that it's true. That's something about which you have to be very careful in this class. Unless you're explicitly told that if something is true, you have no right to assume that it is. So we could have A, B, and C arranged, as I'm about to draw. So there we go, A and B and C, such that AB is equal to CB. But it does not follow in this case that, oops, I meant to say B, so let me make that change. It does not follow that B is the midpoint of segment AC. And why is that the case? Well, the midpoint has to actually be on the segment AC. So we would have to draw the segment AC in this case, and its midpoint would have to be on that segment. I'll call it M for midpoint. So M is the midpoint, but that's not B in this case. So there's no reason to assume that B has to be the midpoint of AC. So yeah, does not follow. Now, inference chains. And this gets us very close to the concept of proof, but I'll hold off on that until the next chapter. That takes a little bit of care how we set it up. Now, typically what we have in this class are not single inferences like the ones that we've considered, instances where we have one statement, thus a second statement. Instead, we have a chain of such inferences, okay, that carry us to some last statement, which we will call the conclusion in the next chapter. But that's what we have. This is what the class is really about. It's about the construction of inference chains. So here in this chapter and on the worksheet, I will have you do a number of examples of these. And typically we arrange these inference chains in column form. The left-hand column will contain statements, and the right-hand column will contain those definitions or postulates, later also theorems, by which each statement follows. And the first statement is always the given. So here is a typical column for you, and you'll do many of these. The left-hand column is labeled statements. Those are the statements that together comprise the inference chain. And the right-hand column, called by, is the definition or postulate that is applied to give us each new statement. So let us look at what we've got. The first statement is 2x is equal to 12, and we call that the given. I mean, every inference chain has to begin somewhere, and I will always give that to you. So in this case, the given is simply 2x is equal to 12. And then number 2. Number 2 supposedly follows from what came before. That is line number 1. So let us see what we have in number 2. It's 2x over 2 is equal to 12 over 2. Notice what we did. We took both sides of the equation in line number 1 and divided by 2. And that's simply the division property of equality, or just, if you like, just division. Okay, so line number 2 does follow, certainly, and what it follows by is the division property of equality. And then now look at line number 3, which says simply that x is equal to 6. And the question, of course, is how did we get here from previous lines? Well, 2x over 2 simplifies down to x, and 12 over 2 simplifies down to 6. Or as we will say, we substituted 1 for 2 over 2 on the left-hand side, and we substituted 6 for 12 over 2 on the right-hand side. So line number 3 follows from line number 2 by substitution. All right, here's another example, a little bit more complex. It says that B lies on segment AC, and that AB is equal to 3, and that BC is equal to 8. Well, remember what I said a moment ago, if you're not given a diagram, draw it. That makes problems like this so much easier. So let's see, what do we have? So we have a segment AC, and we have a point B on that. And I'm not going to draw this to scale. This is just simply to help me understand what has been said. And I'm told that AB is equal to 3 and that BC is equal to 11. Okay, so there's the diagram that goes with the description, and this is the given. Okay, so line number 2. We now say that AC is equal to AB plus BC. That is, the whole is equal to the sum of the two parts. That's the segment addition postulate, which, of course, to use the abbreviation, could be called SAP as well. And then let's see what happened on line number 3. It looks like line number 2, except the AB became 3 and the BC became 8. That's substitution. AB is equal to 3, so we can replace AB with 3. BC is equal to 8, so we can replace BC with 8. And that kind of replacement we call substitution. And then look at line number 4. It does obviously follow from line number 3. 3 plus 8 does equal 11, and that's just simplification, right? We replace 3 plus 8 with 11, so that's substitution again. When you do algebraic work, substitution is very common. All right, so here's a third. So we know that angles 1 and 2 are supplementary, and we know that the measure of angle 1 is equal to 120 degrees. Now, we could draw a diagram in this case, but I don't think it's really necessary because this is mostly just algebra. All right, so line number 2. This supposedly follows from line number 1. Let's see what this says. It says that the measure of 1 plus the measure of 2 is 180 degrees. Well, the reason we know to write that is because we know what supplementary means. This is simply an application of the definition of supplementary. So that's what we find in the by column. And then look at line number 3. 120 degrees plus the measure of 2 is 180 degrees. Notice the change that we made as we went from line number 2 to line number 3. The measure of 1 was replaced by 120, which we, of course, may do because the measure of 1 is equal to 120 degrees. And that kind of replacement, where we have equality, is substitution. So under the by column for line number 3, we have SUBST for substitution. And then line number 4, we took line number 3 and subtracted 120 from both sides. That just is subtraction when you subtract the same quantity from both sides. And then line number 5 was simply what you would have called simplification from your Algebra 1 days. 120 minus 120 became 0. 180 minus 120 became 60. That kind of simplification work we call substitution. And then look at line number 6, our final line. We say that angle 2 is acute, which does indeed follow. If angle 2 is equal to 60 degrees, then it is acute, and that follows simply by the definition of acute. Now, we've seen column-type inference chains with 2 columns, a statement column and a bicolumn. Typically, not in all cases, but typically we'll insert a third column because I find it helpful to do so. And that third column will be the from column. And the from column consists of numbers of previous lines to which our definition or postulate was applied to give us the new line. So let's look at some examples. So we're told that C lies on segment AB, and I tell you what, I'll draw us a diagram because they're extremely helpful. So This says that we have a segment AB, and C lies on that. So there's the segment, there's the point C on segment AB. And then we're told that D lies on segment CB. Okay, so we see the subsegment CB, and we know that D lies somewhere on that. Okay, so there's a diagram that illustrates the given. And then we're told that AC plus CB is equal to AB. Indeed, that follows, right? AC and CB are two parts of AB that together sum up to AB. So that's the segment addition postulate. And we're also told that CD plus DB is equal to CB. Well, yeah, that's true as well for sure. Because if one considers the segment CB, it has two parts, CD and DB. So that's the segment addition postulate again. And notice that the segment addition of postulate was applied to the given, that is line number 1 in both instances. And then let's look at line number 3. This is perhaps the most complex inference that we have seen. It says that AC plus CD plus DB is equal to AB. Well, how did we get there? Well, look on line number 2. We have an instance of CB, right? And then on line number 3, we are told what CB equals. We're told that CB equals CD plus DB. Now, the substitution rule tells us that if we know that one quantity is equal to another, we can replace the one with the other wherever we like. So what happened is this. We took the CB on line number 2 and replaced it by what we're told it's equal to on line number 3, which is CD plus DB. So we end up with AC plus CD plus DB is equal to AB. So what we did then is we applied the substitution rule to lines 2 and 3. So notice that sometimes a particular definition or postulate can apply to more than one previous line. All right, so let's have another example. It says that angle ABC is right. Okay, so let me go ahead and draw a diagram to represent that. And let me implore you again that if you do not have a diagram that has been drawn, draw the diagram. That's why we worked so hard back in chapter 1 to make sure that you knew how to draw the diagram so you could do this. So we know that angle ABC is right. So here is angle ABC. Recall that the middle letter has to be the vertex, so ABC. And recall how, of course, we indicate in a diagram that we have a right angle. We tuck the little square up next to the vertex. And we also know that ray BD passes through the interior. Okay, so here's a ray BD that passes through the interior of angle ABC. Okay, so that's our given, which I now have pictured for us. All right, line number 2 says that the measure of ABC is equal to 90 degrees. Of course, that follows from the statement that angle 1 is right simply by the definition of right. And then we are told that the measure of ABD plus the measure of DBC is equal to the measure of ABC. Let me picture this for you in the diagram. So here is ABD. That's one piece of ABC. DBC is the other piece of ABC, and we're told that the sum of those two pieces is the whole. And indeed, this is true by the angle addition postulate, and that follows from line number 1. Now, let's think about lines number 2 and 3 together. We're told that ABC is equal to 90. We're also told that ABC is equal to ABD plus DBC. And we know by the transitivity of equality that things equal to the same thing are equal to one another. So 90 is equal to ABC. ABD plus DBC is equal to ABC. Okay, so we have the two things, notably the ABD and the 90, that are both equal to ABC. So that follows that they are equal to one another. So there it is, ABD plus DBC is equal to 90. That is the transitivity of equality, and that is applied to lines 2 and 3. And typically the transitivity of equality, because it needs two equations to do its work, will apply to two previous lines. And now let's look at line number 5. It says that angles ABD and DBC are complementary. Well, yes, indeed, that does follow from line number 4, because what does complementary mean? It means that the sum is 90 degrees. So we have that line number 5 follows from line number 4 by the definition of complementary. And that's the end of the show. As for what you have to do on the homework assignment, you have some examples of sort of atomic inferences where you have two statements linked by thus. You're supposed to tell me whether it's a genuine inference or not, and what definition or postulate applies if it is. And then you have a number of inference chains to do, some of them 2-column and some of them 3-column. Good luck.